First, I want to make some comments on one of the homework assignment number 2. This one, actually there is some, relatively big problem I want to talk about. Question number 6. All right. All right. Here, the question is like this. It is ODE with shifted data. So the problem occurs at this part. Data shifting, so this part. So we know, so we use some auxiliary function. So the first step, so then we do the coordinate system switch from one to the other. But when we do this kind of manipulations, there is one little problem. I want to talk about here is the range of your variable, for your variable. Here, our original question. So the domain, let's say domain, the formal name, t, domain for the variable t, right? It's a piecewise function, but you can see the domain for this t is starting from 0, then to infinity. So t-axis, So all this half-axis, from 0 to infinity, that's the domain for this t variable. So we need to keep this in our mind. Then, based on our natural understanding, after you find a solution, your solution function should also have the domain in this half-axis, right? If you change the domain, it's not right, right? If you change the domain, it is not right. So here, we need to really enforce this understanding. But when we do coordinate system switch, then due to some technical reasons, you will see there is a possibility people may change this domain. All right, so let me show you the details, the problem. All right. First, here we do the coordinate system switch translation, right? So there are two coordinate systems, one t coordinate system, the other t tilde coordinate system. The relationship is, this is a relationship. Okay, all right, so let me draw the second coordinate system, t tilde coordinate system. All right. So here, translation, right? So when t equals 0, so not there. So here, when t tilde equals 0, t equals pi. Relationship. So tilde. All right. So here, this is the 0. When t tilde equals 0, so here, let me draw coordinate system in parallel, so we can compare in parallel. All right. This is t coordinate system. All right. 0 is here, Yeah, that's the 0. 0 is here. This point is pi. Then 2 pi. All right, yeah. So then pi here. Negative pi here. Okay, yeah. So you can see. Let's compare in this way. All right. And we know, so draw this vertical line. Initial value given here. Initial values given, yeah. This vertical line, all right? So you can see at this initial value vertical line, in the t coordinate system, it is at pi point. At the t tilde coordinate system, it is at 0 point. All right. Then, let's look at the domain of t tilde. Yeah. So we need to keep track of the domain change. Yeah. From beginning to end. Yeah. Keep closely. Yeah. So we cannot get lost regarding the domain issue. Okay? All right. So here you can see, yeah, the domain for the t tilde, I mean the function, yeah. So we can call this R function, yeah, R function or R tilde function, yeah, you can call it, right? Yeah. All right. So the domain is this part, right? Yeah, yeah, yeah. All right. So then the problem, all right. At this point, it looks fine, okay? Because we haven't started do our computation work, yeah. So we haven't started doing calculation, yeah. All right. Next, when we do calculation, we have some problem. All right. Remember, we need to apply Laplace transform on the functions both sides. Yeah. So here, Laplace transform on this equation, both sides. All right. Then, for the Laplace transform, there is a definition problem. Definition. Yeah. All right. So let me connect my remote control. Yeah. Yeah. So let me bring up the definition. Look at the definition of Laplace transform. Oh, yeah, the next slide. Yeah, all right. We know the integral, right? Yeah. So integral from 0 to infinity e to the negative s t f of t dt, right? That's the definition of the Laplace transform. And we know this Laplace transform so here the problem related to Laplace transform. It is just a tool, right? It is a problem-solving tool. Okay? Now, one specific problem-solving tool. And it has its limitation. Yeah. Any tool has its limitation. Yeah. Yeah. So here we need to understand the limitation of Laplace transform. Yeah. Because what's the limitation? Here we need to, before we understand, because this problem, it took me quite some time to understand. At this point, I do not have complete understanding. So today I raised the question. I couldn't give you complete answer. So I need to, try to figure out the answer. Yeah. So I hope before the semester ends, if I can figure out, so I will let you know. Yeah. Because it is an important question. Okay. It is an important question. So we want to find the, final answer. Well, all right. Limitation of this Laplace transform. Look at the definition here. We can see the limitation. This definition, when you apply Laplace transform on f function, look at the values we need to use for f function. So what values do we use for f functions? Yeah. We use the values. Oh, I need some. We need the values of f of t, yeah, for t greater or equal to 0, right? When t is less than 0, do we use the value? We never touch it, right? And how do you know f function is not defined for t less than 0? You do not know. It could be defined or it could be undefined. Yeah. So, but for many functions, for example, sine function, cosine function. Sine function, cosine function, f is defined when t less than 0. Right? Many functions, e function, yeah. F is defined for t less than 0. Yeah. But here the question is, no matter what value used for f function, it is never used when we apply Laplace transform. Right? It is never used. Yeah? Now, that caused the problem. All right? So here, the conclusion. Yeah. So for this part, based on the understanding at this point, the conclusion is the values for f function when t is less than 0 doesn't matter when we apply Laplace transform, because we never use it. When we take the integral, we never use that part. Right? Yeah. Now look at this function. Look at the, this part. After coordinate system translation, then suddenly we have one part, this part, t tilde less than 0. Okay? So here, t tilde less than 0. Yeah. Between negative pi and 0, so this part is less than 0. So we apply Laplace transform on this function, this portion disappears. It is not used. It is not used. That means its value doesn't matter. Value doesn't matter. It disappears. That means the data corresponding to this portion is gone. Okay? Or you throw away. You, as a problem solver, you throw away part of the data. So this part. You do not need to use it, right? If you do not need to use it, that means you throw it away. Yeah. Okay? That's the problem. So do you feel, based on your understanding of the natural world, when you do things like this, is it risky? When you throw away some portion of data, it is risky. It is very risky. There is a chance this part of the data that people ignore or throw away, it could be very important. You cannot ignore. You have to use it, this part of the data. But Laplace transform based on this definition, you do not need to use it. Okay? Yeah. Then it tells us when we apply Laplace transform for this question, it may not be a good tool. Yeah. It may not be a good tool for this question. We know it is a powerful tool. We like the power of Laplace transform. But due to its limitation, we may lose part of the data when we use this tool. That's the question. That's the question. Okay? Yeah. All right. Yeah. So that's the first part. First part. All right. So then, yeah. So here, the part in my solution, it has some problem. Yeah. So I pose a solution, but my solution cannot fix this hole. Cannot fix this hole. Still, some problem. So today I raised the question. Yeah. I cannot give you the solution at this point. Yeah. I need. So I try my best to find a way to get a perfect solution. Yeah. All right. So let me use this slide to explain a little more. Yeah. So that, yeah, because here, although you see the domain is extended to the negative half of the axis. Yeah. This negative half. All right. Then some of the students throw away this negative half because it's irrelevant, right? When you apply Laplace transform, if you have this part or you do not have this part, the same thing, the same result. Then some students just change this, throw away the negative half, change it to 0. Okay? Yeah. Change it. That means cut off, right? Yeah. Yeah, cut off. Okay? Because from the Laplace transform point of view, you didn't lose anything. When you cut off this part of the data, you do not lose anything regarding Laplace transform. All right? Yeah. But think about it. Laplace transform may not be the only tool, right? Yeah. We have many other different tools in problem solving. Yeah. We will learn Fourier transform soon. Fourier analysis, Fourier transform. Here, I want to compare it with the Fourier transform. For Fourier transform, the definition, you look at the definition, we need to use the negative half axis. We need to use the negative half of the data. We have positive half, negative half. Okay? Then we do not need to throw away, right? Think about it. If you apply Fourier transform on the equations both sides, you need to use the negative part of the data, right? You should not throw away, right? You should not cut off that, between negative pi and 0, that portion of the data, right? Yeah? Think about it. So this tells us the solution. Think about if this statement is correct or not. If a solution of your ODE depends on the tool you used, is it correct? If you apply one tool, you get this solution. If you apply different tool, you get a different solution. Do you think it's correct? When you apply a Laplace transform, you get one solution. Then, yeah, after we learn the Fourier analysis, we can switch to Fourier transform. Then you will get a different solution. Is that acceptable? That kind of behavior acceptable? So your solution relies on problem-solving tools. That's not right. Yeah. Yeah. Because solution is a solution. Okay? The solution, the function follows the given ODE. That's the solution. It doesn't matter which tool you use to find the solution. Okay? Yeah. So all the tools if those tools have no problems, no limitations, they should find the same solution. Otherwise, one of the tools should have some problem. Okay? Limitation. Yeah. Whatever you call. Yeah. Here, we are facing this question. Okay? We are facing this question. All right. Yeah. Yeah. All right, so here we compare Laplace transform and Fourier transform. Fourier transform, yeah. Here I put a formula here for comparison purpose. Yeah. Later we will learn. So you see, different formula. Laplace transform, we only use the function values at a positive half axis. Okay? Only one side of the zero, the right-hand side part of the data of the function values. Okay? Yeah? All right. But for Fourier transforms, when you calculate the coefficients, both sides, right? Yeah, although here, this formula is because we know the Fourier transform here is for the periodic function. Yeah. Applied on the periodic function. Periodic functions. Yeah. Yeah. But we can stretch that L, right? Yeah, we can make that L sufficiently large to cover the main part of the f function. Yeah, hopefully cover, all the data of the function. But sometimes we cannot. Yeah. But later we have another modified tool we call a Fourier integral. Fourier integral, we can cover all the real axes. Yeah. So here, this Fourier transform formulas, we just cover limited portion of the real axis. Yeah. All right. But both part, yeah, positive side, negative side, we cover. Okay? Yeah. So in this way, you can see we can pick up the negative half of the data. Yeah. We should not throw away. We should not throw away any data. Yeah. That's the problem. That's the main problem of the question. Okay? Yeah. Yeah. Yeah, I noticed, yeah. So I noticed, some students using that way, yeah. Probably, so they're based on the solution from the solution manual of our textbook. Yeah. Yeah. I have the solution manual. So I compare my solution with the one in the solution manual. Yeah. It throw away the negative portion. Yeah. It does not explain, but yeah. Because Laplace transform, technically, yeah, here, technically you don't need that part. Yeah. So as a simplification, then it just, kick it out. Yeah. Due to the technical reason. All right? Yeah? Yeah. Yeah. Then, after that, yeah, then the data, because you lose half of the data. Okay? We know the meaningful data from negative pi, positive pi, the meaningful data is in this 2 pi interval. The length of our non-zero data is in this 2 pi interval, yeah, but Laplace transform does not use the negative half. It only uses the positive half. All right? So then, after the solution, yeah, because when you do the inverse Laplace transform, you cannot recover that negative half, right? Think about it. You apply inverse Laplace transform. So your inverse Laplace transform cannot recover this negative half. It's gone. So the final solution, yeah, So here, let me talk about the final solution. Due to this reason, the final solution. Two cases. Yeah. So based on my grading, I saw two ways our student use to handle this situation. All right. Two ways. Yeah. The first way, yeah, because after you inverse Laplace transform, then you need to shift your coordinate system back to the original coordinate system, right? You need to do another shifting operation, going back. But when you do shifting operation, so this portion needs to be shifted, right? That portion needs to be shifted back, all right? Yeah. So the first way, the first method, okay? Yeah. Here, yeah, because it's hard to use words to describe, so I can only draw diagrams. All right. So when those so here we use axis. All right. Yeah. All right. But because your final solution, you need to shift it back. But you have the data between pi and 2 pi. And there is a gap between 0 and pi when you shift it back. Because your inverse Laplace cannot recover that part. So when you shift it back, actually, those students use the same function, all right? Yeah, because for this half, you have a function, right? Yeah. F1, yeah, let me call this function F1. Then those students use the same F1 function for this part. Yeah? Because that F1 function is defined. Then just use the same function, like extension. Extend that function for this half. Okay? So that's the method 1. Yeah, solution. Yeah, most students use this way. Yeah. Extend that F1 function, right, to the missing half. So you have the values, yeah, but you do the extension. Okay? Yeah. The method 2. Method 2. No. Still, this missing half. So finally, you need to, yeah. All right. So for this portion, F1, right, there, this portion, yeah, because, you know, yeah, so this didn't put 0, this part. Then, not right, right? Suddenly, you know, the solution function suddenly becomes 0 at this part. Yeah. Think about that. So these two ways, yeah, not quite right. Yeah. The reason is because the limitation of the Laplace transform. Yeah. If we use other tools, we can avoid this problem. Okay? All right. Yeah. Then the solution, the possible solution. Yes. Yeah. Because we need to, for the problem like this, we need to try to find the right solution, right? Yeah. We need to, as a learning process, we need to find the right solution at the end. Okay? Yeah. Yeah. If we cannot do it, at least we need to try it. Yeah. Even if we cannot make it, at least we need to try it. Yeah. So my plan is, yeah. We do not have much time in the remaining of the semester, about 1 month left. Yeah. Yeah. So I have two ways in my mind to complete the solution of this one. Yeah. Right. The first way, Fourier transform. Yeah. So we will learn Fourier transform soon. Yeah. So after we learn the Fourier transform, let's apply the Fourier transform to solve the same problem. Yeah. It can be done. Yeah. Fourier transform very powerful. Okay. Yeah. So we have the confidence, although the solution expression may be different. Yeah. It's not important. Yeah. The solution formula may not be, because Fourier series, that's the form. Yeah. Yeah. But definitely we can find a solution function in that form. So that's one way. Yeah. Second way, yeah, because if we do the Fourier transform way, that means we throw away Laplace transform way, right? Yeah. We drop it. No? We do not apply Laplace transform for this particular problem. That's still, it's a pity. Yeah. So I feel, because Laplace transform is such a beautiful mathematical tool. Yeah. I do not feel comfortable just throw away Laplace transform for, this kind of relatively simple ODEs, right? Yeah, this ODE is not very complicated. Pretty simple. So we should not give up like this. Yeah. So we need to try to rescue that Laplace transform, that powerful tool, beautiful, powerful tool. We need to rescue, do something, try to rescue it. All right? Yeah. So, yeah. So that part. So I try to do it. Yeah. I don't know if I can make it or not. Yeah. But I feel it's an interesting question. So in math, situation like this, actually, it's an opportunity for math people. Okay? It's not a bad thing. It's a good thing. When you hit something, okay? Yeah. Hit a wall, obstacle, yeah, something. It's an opportunity for us. Yeah. We are problem solvers. Yeah. So when we find some new problem, that's our opportunity. Yeah. So we want to find a solution. Okay? Yeah. All right? Yeah. 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 So here I have an idea, because I still, so my, for our method number two, I still want to apply Laplace transform. Yeah. But we need to learn which part of Laplace transform causes the problem, right? Which part of the Laplace transform causes the problem? In the definition, this part causes the problem. The bottom part of the integral definition. Look at the integral limit from 0 to infinity. That's 0. That starting point, 0. That caused the problem, right? Yeah. Because of this definition, cut off a portion of the data. Yeah. In order to fix it, can we change this lower limit of integral? Can we extend the definition of Laplace transform, stretch it to cover the data? Is that reasonable way? Yeah. If technically, no problem, yeah, because when you modify the definition of the Laplace transform, so you stretch the lower limit of the integral, you need to consider technically if there is any problem. If there is no technical problem, or all the formulas of Laplace transform can be, have no problem for the new version of Laplace transform. Yeah. Then we can try. So we stretch it, covering our data, covering all our data, right? Then apply the same formulas. Now, we need to make sure all the formulas we use must be perfect. Okay? No technical holes. Must be perfect. So we can apply those formulas and see if we can find good solution. Yeah. All right? Yeah. So I do not assign this question to you, because you have too much work to do. Yeah. Okay. If some of you are interested, you can try. Yeah, but here I just raised the question. If I find the answer, I will give you a report, give you an update. Okay, all right. Yeah. Update, the best thing is if I can write a document. Yeah, I post it. You just download. You can study even after class. Right? Yeah, it's a good example, right? Yeah. So that's my plan. Yeah, I try my best. Yeah, because if I use Fourier transform, then we get around it. Yeah. It's not. We just get around it. Yeah. But here, we still, we want to preserve the power of Laplace transform. Okay? Yeah. Yeah. Such a great tool. So we want to use it. Oh, another thing I forget to mention regarding the Laplace transform in my grading. Another important aspect of Laplace transform. Close to, I spent too much, but it's important, very important, because in our learning, right, situation like this, in our learning, it's very important. Yeah. Knowledge part is important, but in this problem solving, in the real world situations, you may have a lot of problems like this. Okay? Yeah. You cannot find solution from the textbook, or the solutions provided from the existing books, literature, not correct or not right. Okay? So you need to figure out your own solution. So here, right now, it's this process. Yeah, because the solution manual, I feel, not correct. Okay? We lost the data. That's not correct. Okay. So we need to find the correct way. Yeah. So I use this example. So actually, this is a good example. We can learn something, right? Yeah, learn something. Yeah. All right, yeah. But there is another aspect, because before the break time, we do not have much time. So let me just use the remaining 10-something minutes. Yeah. Talk about another useful thing I observed in my grading regarding Laplace transform. Yeah. Here we know this function, it is a piecewise function, right? Yeah. Piecewise function. So here, and Laplace transform, this tool is a perfect tool for piecewise functions. Yeah. One of the reasons people use Laplace transform to solve ODEs because it can handle piecewise functions quite well. Yeah. That's the strong point of Laplace transform, right? In my grading, I noticed several students didn't use didn't use Laplace transform. Okay, yeah, they didn't use. Right. So in this situation, yeah, so here we have piecewise function. So let me draw the function definition. There are two pieces. Okay, all right. From 0 here. 0, 2 pi, first piece, okay, solution like this. Okay, then second piece greater than, yeah, so this part 0. Okay, two pieces, right? Yeah. Piece 1, piece 2. All right. Then those students, they used a natural way to solve these two pieces. Right-hand side function, two pieces. All right. Piece 1, yeah. So they solve this ODE by separating these two pieces and solve the ODE independently. It looks pretty natural, right? In piece 1, yeah, piece 1, because you only need to consider the first function, right? Yeah. Piece 2, you use the second function, right? Two functions. Piece 1, piece 2. Yeah. All right. Yeah. Without using Laplace transform. In that way, if you separate the two pieces, we just use our regular way, homogeneous, non-homogeneous, YH plus YP. We can do that, right? Yeah. Yeah. No problem. All right. But there is one. Yeah. Yeah. So if you dig deeper, yeah, dig the, solution deeper, so you will see some big problem. All right. In piece 1, your initial value is given in piece 1, right? So initial value, this is pi is here, pi. Yeah. So when you apply the initial conditions, in piece 1, no problem. In piece 2, what's the initial some people may argue, piece 2, then you find this value. From piece 1, then as the initial value, right? Yeah, yeah, you can do that, right? Yeah, yeah, initial value. Piece 2, yeah. Then see, yeah, but those students I didn't see they use this value as the initial value of P. Yeah, because remember in our homework assignment number 1, right? Yeah, now we have that fission. Intermitting fission, right? In that one, so we use initial value at the end of the first period. When we start the second period, we have the initial value from the first period, the end point of the first period. Yeah, but those students didn't use this way. Yeah. Piece 2, yeah. Piece 1, piece 2. Okay, yeah. In that way, yeah, it looks all right, right? Yeah, in that way, yeah, it looks all right. Yeah. Yeah. But so here you can see, we have several ways to solve this problem. Yeah, if we get a correct solution, all different ways should give us the same solution, right? Maybe the formulas look different, but the function values should be the same. Yeah. All right. So, yeah. All right. Yeah, yeah, but I have to be realistic. Yeah, because for the last month of the semester, everybody is very busy. Yeah. for myself, I'm also very, very busy. Yeah. Because I have research project to do. Yeah. This month. Yeah. You know, yeah, extremely busy. Yeah. That means I may not be able to complete what I want to do. Yeah. Yeah. It's hard for me. Yeah. But I will try my best. Yeah. 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 But here, today I use approximately 1 hour here to make this kind of comments. Yeah. Yeah. For some of you, yeah, yeah, because you want to solve the real-world engineering problems. Yeah. Real-world engineering problem, most of the right-hand side R functions are piecewise functions. It's very common. Yeah, for the engineering problems. So that's why Laplace transform very important. Yeah. If not Laplace transform, yeah, so we have other ways to solve. Yeah. Yeah. Fourier transform, also good for piecewise functions. Because integral, all integral-based methods, yeah, good for piecewise functions. Yeah. Yeah. All right. All right, yeah, so let's take a break. When you come back, let me try to complete part B. Part B, not very long, yeah, so only 2 topics, yeah. So we can, yeah, you know, if we can complete, so next time we can start part C. Yeah. Oh, regarding the homework assignment number 3, yeah. This week, let me see, this weekend, if I use another week, let me see if we have enough time to, yeah, yeah. Probably I have enough time, yeah, because this week we just started April, right? Yeah. This week, Thursday, yeah, we just started April, so next week we have the first, we have the homework assignment number 3. So then, in the middle of the April, we have last assignment. Yeah, probably we're fine. Yeah, probably we're fine. But this week I need to give you quiz number 4. Quiz number 4. Yeah. So before you do homework assignment number 3, let's do quiz number 4 this weekend. Yeah. Yeah. Then next week, you get a homework assignment number 3. Yeah. Yeah. Then after 2 weeks, let me see. Yeah, every 2 weeks. Yeah. Yeah, but for last assignment, I may push a little earlier. 2 weeks too long. Yeah. So after I give you third homework assignment, the last one, probably I need to give you a little earlier than 2 weeks. 2 weeks of the time after you get a third assignment. Third assignment, probably plus 10 to 12 days, I need to give you a fourth assignment, so that before the end of the month, we can complete the last assignment. Yeah. So that's the plan. Yeah. Okay. Yeah. All right. Let's take a break.